So, hello and welcome to this course or continuation of the course, all right, but well, just welcome then. So we're done with chapter 3, we skipped 3.5, which goes into the continuation course. Also, all of chapter 4 goes into the continuation course. So chapter 4 is a bit like, somebody invented at some point in the history real, positive numbers. But then his student needed something to do, right? So there came the negative numbers also, and everything got more complicated. So it's the same with the measures. And the measure of something is a positive number, it's not a complex number. You don't have a box with, size 2 pi I. But by the way, so it's like that. So chapter 4 is about, then somebody, developed the theory for complex valued or also signed measures, meaning they can be positive and negative numbers. So having trash talked it a bit like that, I want to say that it's also, it's a beautiful theory in chapter 4, beautiful. So, there's like fundamental theorem of calculus. If you integrate the function f and then differentiate it, you get back f. Nice, but for which functions? In order to be able to differentiate, you need something which is C1. So then which means the f needs to be a continuous guy. But you can take many functions which are not continuous, integrate them, and get a primitive function which still exists. So in a way, differentiability does not need continuity of the derivative. So one of the really nice results there in chapter 4 is like you find like the perfect extension of the fundamental theorem of analysis. But that is for those of you who want to do the continuation course. So here we're not doing that. We're going to jump straight to chapter 5, which is about basically partial integration. And to start off, I want to start with an example, but I'm going to make sure the camera is properly zoomed first. Okay, so to get the topic of partial integration started, I start with a rhetorical question. What is the infinite sum a and n? So think of an is usually what we denote the sequence, right? N goes from 1 to infinity. But what if you have two sub-indexes here, m and n, that both go from 1 to infinity? So basically, you have values on a grid of integer points, right? And so, yeah, what is that? Is it... here, this is something we can understand, right? So you sum from first in n up to infinity. So for every n, this is just summing a sequence. And then you do the same for n. We get some number. But is that number the same as this number where I flip the order? And is that the way how we should define this object? So with the tools of analysis 1, yeah, you would be kind of lost here. You could maybe come up with some theory that under some conditions, this one is equal to that one, and we define it like this one. The beauty of integration theory, the way we learned it now in the abstract framework, is that we can interpret this as an integral, and its meaning, we don't need to define it, it's already defined, right? So we do not need to choose either of these definitions and yada yada, because we can think of this as integration, and then everything is solved by this massive machinery of the Lebesgue integral. So every time you have a measure mu and a function a, the integral of a exists, given that you get finite numbers for the positive and negative parts, right? So then that is the natural definition of what this sum means. Because well, we take X, the big space, we n cross n, so this grid of points here, and then mu, the counting measures, you just count points. And then you realize that if I have like a simple function here, and of course, a, m, and n, which is a multiple index sequence, we think of it as a function on this, and then we can integrate it. And if you have a characteristic function here of, you know, this point, and the value is 2, it's very easy to see that, I mean, and the integral is going to be 2. So for finite sums, this is, like, for simple functions, a, this turns into a finite sum, which is equivalent to what we expect here. So this is the most natural definition. Okay, so now we defined it by using the Lebesgue integral, but then the question here would be then is so the next natural question now is, okay, once we've defined it like that, I mean, it should be intuitively at least equal to this guy and also equal to that guy. Is that true? And the answer is no. Most of the, well, sometimes not, okay? So let's look at a very simple example there. So let me just write sequence values next to the point. So let me have here +1, +1, +1. Here I do -1, -1. Maybe this is not seen properly. Okay, so suppose we define a sequence like this. We have 1s on this diagonal, -1s on this off diagonal, and then 0s everywhere else. Well, what we get here, so let's say this is here the m axis, and here we have the n axis. So if I first sum in m, I'm getting 1 for this first row. And then here I get 0, 0, and 0, right? So this object here will now be equal to, let me write it here, equal to 1 for this choice. What happens if I sum in this direction? I get 0 all the time, right? So this inside sum is always 0, and then the outer sum is also 0, so we just get 0. Okay, so here's the problem. What is the problem? Well, you know, cut to the point. If you remember what means integrable, for the integral of a function to exist, you need at least the positive or negative part be finite. Here the function a is +1 on this diagonal, and if you integrate that, you get infinity, and then it's -1 on this off diagonal, and you get infinity again. So the positive and negative part of the functions a both have infinite integral, and therefore the integral doesn't exist. That's the problem. So the only like major theorem we have left is called Frobenius theorem, and it says that as long as, you know, this integral, as long as an integral in several variables exists, then you can do partial integration in which order you want. Okay, so that's what we're aiming for here. And this example then shows that this is necessary. Now, okay, so this is just an example on n cross n, but usually we do integration on r times r, or more general abstract spaces x times y. And that leads to you know, even to get a proper framework worked out, we need to get through some technicalities first. So if we now want to lift this to the Lebesgue setting, so now here we can ask the question, if I have an integral of x and y, and then I have the Lebesgue measure in two variables which exist, we introduced that in chapter 1, then I can integrate this, given that these integrable and measurable and all of that. And now I can ask myself, is that the same as doing a one-dimensional Lebesgue integral in the x direction? This gives me a function of y. And that I can do a Lebesgue integral with respect to one-dimensional Lebesgue measure again, and I get some number here. And of course, I can flip the order, right? So are these two the same now? Of course, from analysis one, you learn this, that, yeah, this is how we evaluate these type of integrals, but why would they be the same? I mean, even we're going to get some problems with measurability here, right? Because where is he measurable? Maybe on the Borel sigma algebra in 2 dimensions. Okay, but then here, what I'm doing is I'm freezing y, and then I'm integrating in x. Is that Borel measurable then? I mean, so does this even exist? Or if it's Lebesgue sigma algebra, you know, I have a 2-dimensional Lebesgue sigma algebra, and then I have 2 one-dimensional ones. And worse yet, suppose now you have a function on some more general space. So R2 is like R times itself, right? The Cartesian product. And if you have some abstract space X, you can do the same. You consider just all pairs, right? So this is equal to the set of pairs X and Y, such that X is from X and Y come from Y. All right, so now we can think of functions here. And we have some function there. I can, of course, and then I have a measure on the X space. Then we call that mu, so I can integrate with respect to X. And then maybe I have a measure mu on the other space Y. So I can integrate with respect to that also. Now I have myself a number here. And then I want to ask if this is equal to the integral of f with respect to what? I mean, what? Here I got the 2-dimensional Lebesgue measure for free because we've defined Lebesgue measure in various dimensions. But what's, I mean, I cannot even introduce what I should write here, right? Because I don't have a measure in X times Y. What's the proper name for that? X times Y is not a suitable name. Well, yeah, no, it's slipped my mind. I'm going to call it X times Y, Cartesian product. Right, so here's an array of problems that we have to work out. Once we do that, so what we're going to do here is we're going to get something called the product measure, right? And then we can introduce him like this. And then for Venus theorem is saying that this whole formula holds true, at least the fact that it's integrable. And then that will be the end of the course. But to get here, it's a bit of a long walk. Yeah. So we're going to get technical. Okay, so before we can integrate, you know, this integral here that we want to introduce, we have to determine whether he's measurable or not. Well, we don't even have a sigma algebra on the product space X times Y. So the setting is always this now. We have an X, sigma algebra A, measure mu, and another space Y, sigma algebra B, and measure mu. So we need to start with, we need a sigma algebra on X times Y. And that's luckily enough, very easy to do. We're going to borrow some ideas from chapter 1. So how could we possibly define a sigma algebra on X times Y? Well, we have this proposition, you remember we used when we introduced the Borel sigma algebra. If you have some bunch of basic sets, there's always a smallest sigma algebra which contains those sets, you know, whatever those sets might be, a collection of sets. So what, of course, we want to know a sigma algebra on X times Y that somehow connects with A and B, right? So here's my X, here's my Y. And what can I do then? What's a natural candidate for some of our building block to a sigma algebra? Well, what I have is I have like, I'm just going to use intervals to denote like arbitrary measurable sets. But I have here measurable sets, let me call them A. And up here I have measurable sets B. But what I can do is consider the product set, right? And what I get then is a rectangle. Of course, if B is not an interval, but maybe a K consisting of two intervals, it looks like this. It's still a product set, right? And if A has a different interval here, now it's going to look like this. But you know, this is not any arbitrary set, they have a very specific form. This would be the natural candidate, right? To build a sigma algebra that's like rooted in sigma algebra B and A. And that's exactly what we're going to do. Right, so A times B will be the smallest sigma algebra on X times Y that contain all product sets A times B, where A is in A and B is in B. And then, I think I mentioned this already. So here the Borel sigma algebra is much better than the Lebesgue sigma algebra in the following sense. So here's the first example. This is good news. If I take the product of the Borel sigma algebra with itself, I get Borel sigma algebra in two variables. And this is actually not hard to see. Well, maybe it's not that obvious, but anyway. So usually when we want to prove set equalities, we end up proving two inclusions, right? So one is subset of the other and the other is subset of the first. So let's start with, okay, so I have to prove that this is a subset of that. And I have to prove that that is a subset of this, right? So let's get going with this one. Sorry, I've completely forgotten that there was some details hidden here. Let's start with the easy direction, okay? So we're gonna do this first, then we do this inclusion. So what do we want to prove? We want to prove that he is smaller than that guy. Now this is the smallest sigma algebra generated by open sets in R2. This clearly is a sigma algebra, so if we can show that it contains all the open sets, we're good, right? Because this is the smallest one containing all the open sets. Now, how does an open set look like? Oh, something like this, okay? In R2. So how can I prove that this open set is now in my product sigma algebra, where I'm only used to, use product sets as building blocks? Well, it's very easy. You just, you see that you can write the open set as an infinite union, countable union of product sets. And one easy way of doing that is just, let this be an integer grid. And then all boxes which are inside, you just color them and call them, A1, A2. And then you refine your grid, okay? And on the next level, all the boxes that are now completely inside your open set, color them, you give them names, and like that, you're going to get a countable sequence of smaller and smaller product sets whose infinite union becomes this guy. All right, so the product sets are in here. I do the infinite union. I'm still in here because I'm allowed to do infinite unions in sigma algebras. Therefore, this open set that was arbitrarily is in here. Done, right? And this is a sigma algebra containing all open sets, and this guy is the smallest one. So then we have this inclusion. Now for the reverse inclusion, okay, so let's do that here. I need to do the same trick, right? So I need to consider an A times B. These are the building blocks, right? So I take one from here, where both are Borel. By the way, of course, it's a poor choice of symbol. This is a B, and here's a B. It's not the same B. This is B for Borel. Here's the B like coming after C in the alphabet. Sorry about that. You have to live with it. All right. So here I have a product set, which are the building blocks of him, and now I have to show that he's in here. So it's both of these are Borel. It's kind of intuitively it should be in here, but how do we actually prove it? It's not that clear. So actually it turns out that it's easier to just focus on one of them at a time. So it's easier to show that A times R, which would be, okay, so if I had painted a picture here, there's an A is here, B is here. So now A times R would be like, I just don't care about this restriction in B, and extend this to the whole like corridor, right? But then I can do the same. If I'm able to prove that he's inside, then I can also prove by analogy that R times B is inside, which would be, you know, this set, okay? And now you see it, right? So this guy here in the middle that I'm interested in is actually the intersection of these two. So that's the first realization. But still, we have to show now that he's an element in here. How would we do that? Well, the easiest approach would be to do something just similar. So like how these arguments always run, how this one ran. So we would then say, okay, okay, I had to think a bit again. So it's kind of easy to see that if I take the Borel sigma algebra cross R, actually technically you need to prove this also, but that this is the same as the sigma algebra generated by all open sets times R. This times R remains fixed, so it's like adding a second dimension that does nothing. So you know, this and this are the same by this argument, right? So this is a sigma algebra, it contains all open sets. The first coordinate and here. So, yeah. So this is an easy identity. And now that you have this, you see that, aha, a U times R, if U is open, R is also open. So this is an open set. So this is a sigma algebra generated by open sets. But this is the sigma algebra generated by all open sets. So then it has to be bigger than this guy, right? So this means that the Borel sigma algebra times R is a subset of the Borel sigma algebra in two variables. And then we conclude that as long as A is Borel measurable, adding an R to it, we land in the Borel sigma algebra R2. Now, that's not how they do it in the book, but I show this because it's a bit more easy to visualize. In the book, they work with, so the Borel sigma algebra, whatever dimension, you know, is based on open sets. Open sets are connected with continuity. So we have these results from chapter 1. I think that anytime you have a continuous function, it is Borel measurable. Doesn't matter dimensions. So if you now consider the projection, yeah? You take a pair here in x times y and just project it down on x. Okay, this is a function from R2 into R1. As such, it is continuous, yeah? It's a pretty stupid function and therefore measurable. Now the pre-image of, if I have a set down here, A, and I do the pre-image of that under this stupid function, well, I'm getting one of these corridors. So that's a different way of seeing it, which is faster, but maybe less intuitive. But anyways, so okay, that wasn't so easy to show, but nevertheless, it is true, and that's good. Now the bad news is that this is not the case for the direct sigma. Actually, so what we have, if we agree to call the, you know, technically I should write m lambda 1 star for the outer measure, remember, right? But let's just agree to call this m1. And then we have m1 times m1. Now I have a sigma algebra in 2 dimensions. And it turns out that he's smaller than, but not equal to m2. To see that this is actually just an exercise, I'm not going to do the details, but so here is a sigma algebra based on product sets. You can, oh no, the wrong blackboard. Okay, so you use this trick again to see that, well, if I can show that sets of this form where these Lebesgue measurable in one variable are in here, then I'm good to go. And that's not so hard to see, but you kind of need to then know that no, sorry, I was wrong again. So this is not clear at all. I mean, yes, you should use this trick. The problem is, if you remember the definition of measurability, and I'm not going to write it up, just pause the video, think what was the definition. You realize that you need to check an identity, but all the numbers in this identity is going to be infinity. So that's not, so yeah, then what you need to do is actually to consider A times some smaller, some growing sequence of finite sets whose union is R, and show that they are measurable in here, and then that this is the infinite union. Yada, yada. It gets long, and here we actually need something we haven't proven yet, that namely that if you integrate this, how do you evaluate the measure of a two-dimensional set that is a product set? Is it the, you know, do we have lambda 1a times lambda 1b equals to lambda 2a times b? Yeah, we have that, but we haven't shown it yet. So we can't even use that, and then the whole thing just gets messy. And to prove that they are not the same, you need something about projection. So I'll just drop this thread by now, but I'll tell you that this is how it is. And hopefully I'll get back to it if I weave to it. But anyway, so let's get on with the exciting details of so now we have a sigma algebra. We're going to discuss measurability of functions, and also specifically, you know, if you want to do partial integration, measurability, if you freeze one variable and you know, think of it as a function in the other variable. All right, so if we have a set E in x times y, so let's say something like this is my E, here's my x times y, then I'm going to introduce two very natural sets which are called sections. Here it's a bit easy to get confused. So the first one is, okay, let me freeze some x here on the x-axis, and then I just consider all the points that are inside E with x comma y, which means that we set EX with some index x is actually a set sitting here. Well, it's a subset of y. And similarly, EY, if I freeze some y here, I'm getting this set, right, which I then project down here. So this gives me a set EY in X. Now, another thing that you have to keep in mind or note here, why does this guy stand up and this, why is this upstairs and he's downstairs? Because if you would put both of them downstairs, you still separate them, okay, here's X and here's Y. But what if you want to give them a concrete value? So if here you want to look at E1, so 1 is there, or E1 with the 1 upstairs, it's here. If both of them were down, we would get conflicting notation once we replace X and Y with concrete numbers. So that's why this is up and this is down. What you do if you have 3 variables, I don't know. But anyways, this is a way to deal with this 2 variable situation. Of course, 3 variables, you use induction to construct it. But anyways, so that's not even touched upon in this book. But okay, so now we can start asking interesting questions like, okay, if E is in the product, sigma algebra, are these guys measurable in their respective sigma algebras? Answer is yes. But before we get there, let's also discuss functions, because now I have a function. This is a level set of some function f, that has values on the 3rd axis that we cannot take. Okay, so if I have a function now f on the product set with values in R, then I can do something which almost looks like a complete stupidity. I define fx parenthesis t as f of x comma t. So what's the difference here? Well, technically this is a function of 2 variables. Here x goes into sub-index, so you think of it as frozen, and now you have a function of 1 variable. So what happens here is like if this is my x, then now I don't move that, I freeze that, and I have a function of 1 variable. And this is very useful notation, because then I can ask questions like, okay, if the 2-dimensional guy or 2-variable guy is measurable and I freeze my x, is it still measurable now when I just let one of the dimensions be a free variable? And of course, vice versa, we need a notation for freezing y, and then with the same idea as before, we put the y upstairs. Okay, so the lemma here says it's the best of all possible scenarios. If you have a set like this in the product sigma algebra, then EX, the section is in B, EY, the other section is in A for all XY in their respective spaces, right? I don't even specify that. Similarly, if F is measurable with respect to the product sigma algebra, then the section FX is B measurable and the other section is A measurable, right? So this always works flipped. If I have Fy, then I'm talking of A measurability, but Y is in B, right? Or the Y space. Just have to keep this separated. It's easy to get confused sometimes. And the proof is one of these like dumb ones that doesn't say anything. It's not hard. I'll write it up. Okay, now, again, so you had a lot of experience in chapter 1 practicing these kind of like Godot-Skaft, I don't know how to translate that. So pause the video and just think, how would I prove this? Yeah, it's not a constructive proof. That's a hint for you. And okay, here's how you do it. All right, I'll just write this. You introduce F, which is the set of all E's, which has the two properties you want here if you look at the first statement. Now you show that this is a sigma algebra, which is very easy because he's a sigma algebra and he's a sigma algebra. So this property is just lifted here. Of course, you have to do the computations. There's no resistance whatsoever. Now it's a sigma algebra. Does it contain the product sets? Well, obviously it does, right? Because if I have a product set, you know, A times B, what could be a section here? So this is my E now. Now I consider EX. Well, I have two possibilities. Either X is here, and then I get B. Or X is out here, and then I get the void set. And either way, I'm in B. Same with EY. Either my Y is like here, and then I get A, or Y is here, and then I get the void set. Okay, so this is a sigma algebra that contains all product sets, but this is the smallest sigma algebra containing all product sets. So he must be a subset of he. Hence, every set here has this desirable property. Ta-da! Wonder if McDonald's have open vacant positions. Okay, and then for the second part, it's immediate, yeah, because we just have to realize that, I mean, so now we're going to look at sets like f of fx t less than some number, I think I also used to call it t, let me call it n now. Yes, we're interested in whether this is measurable or not in B sigma algebra, but then you realize that this is just, if you look at the set f x comma y less than m, now you get a two-dimensional set. Okay. Maybe it's easier to just call this y now, okay? So I want to prove that this is a measurable set, right? But this is measurable because f by assumption is measurable. So this is measurable. But then you just realize that if I take the x section here, you know, I'm getting this set. So in fact, here the second row follows by the first part of the lemma. And now actually this gives us, I'll just squeeze it in here. This gives us now with this lemma, we have now an easy way of seeing that these two are not the same. So how do we do that? Well, we just need to construct a set which would be, let me see where it should be. So it should be not in here, but it should be in there, okay? So then this guy will be the bigger one. And what are we going to do? We're going to do the following. So just take some set. I don't know how to paint a horrible set, but take a horrible set, well, a set which is not Lebesgue measurable in one dimension, and consider now the set E cross R, right? So this is not going to be in the product Lebesgue sigma algebra because if I have this set and I take the section, you know, you freeze the y variable to 0, you're getting back E, right? Or for any other value, now you're getting just the void set, right? But here you're getting E. So if E is not measurable, Lebesgue measurable, then this cannot be the product sigma algebra because that would otherwise violate this lemma, right? So here's a set which is not in here. However, if you remember, Lebesgue measure is complete. We never went into completeness, but we proved this property. I used the only completeness property that I actually used is that if a set has outer measure 0, then it has then it is Lebesgue measurable. So any set with measure 0 is going to be in here. Well, this is clearly measure 0 because it's a subset of the real line. The x-axis, so to speak. The x-axis has Lebesgue measure 0. That was some exercise back in chapter 1. Okay, so yeah, this set will be in here, but not in there. Okay, good. So we sorted out everything about the sigma algebra's measurability of functions. Now to move on, we just need a measure on this new sigma algebra. All right, so here we meet a bit of more resistance. So what would I want from a measure like this? Well, the only thing where I could expect to know something is if I apply my product measure to a product set. Because how do we even, how do we generalize the idea of size to higher dimensional things? We just multiply, right? Various dimensions. So, like the rectangle is the base times the height. A box is the area of one of the sides times the thickness, So just building on that idea, the property we want is this. So how would I build such a measure on the sigma algebra A times B? That's a very complicated sets in there. We have learned that sigma algebras are huge. So to construct a measure here, unfortunately, well, luckily it's not that bad, but we need to get through some technicalities first. So what we can do, actually, okay, I'm going to tell you what we're going to do. We're going to do like this. So this is the integral. So here again, here's my set E. I want to give it some size. Okay. And if I freeze my X, well, I have this section, right, which I project down here. And that's going to have some size nu. Right? So nu EX, that's the size. And now we just use this like partial integration idea that if I integrate this, the size here over the full space X, I should get somehow, at least intuitively, the size of the set E. So I'm going to integrate this thing against the mu. And then, of course, this is there's an unbalance here, because why would I start with just taking sections in X? I could do it the other way around, right? I shouldn't discriminate. It's very popular these days, not discriminate. So you cannot discriminate the y-axis. And luckily, in math, we don't do that. So this formula is true as well. But before we get there, here are problems arising, right? Do we even know that this is a measurable function? So, okay, stop to think about it. For each x, E of x is a set, mu of E of x is a number, so this is actually a function here, right? So at least if mu and mu are, if u mu are sigma finite, and as I've said many times, I don't care about non-sigma finite measures, but if ever you bump into one, remember that maybe you have to be careful using convenience theory. Okay, but as long as they are sigma finite, so these guys are measurable, so at least these two formulas here make sense. Okay. And it's another one of these stupid proofs. Okay, so what do we do? Proof. So we want these guys to be A and B measurable? Well, let's start by considering a product set. So if this E is A times B, then as I said before, we have two choices here. Either this guy is B or it's the void set. So now I have something which is 0, then take some value on B, and then it's 0 again. Yeah? So this guy here would be 0 up something. So here's my set B, and here's mu of B. Right? If I consider this function with E being equal to A times B. And that is measurable because the level says, you know, this is a simple function, but B is measurable. So, okay, the product sets have the property we want, and now I'm going to introduce F. Det måste fan vara något viktigt, för nu är det andra gången du avbryter min föreläsning. God damn it. All right, so let F be the set of all E such that E has property we want. Okay, and now we're going to prove that this is a sigma algebra. We already proved that it has the product sets. So it's a sigma algebra containing the product set, hence A times B is a subset, and hence every set in A times B has the property we want. Yeah? So this type of proof, they always follow this blueprint. Yeah, I hope this pattern is clear by now. So that's the, yeah, all right. The details, of course, are more carefully written down in the book. Oh, and here, of course, I implicitly assume that this is a finite number, so this works in the finite case, and then the general case, sigma finite, you just take some limit process. You have to use monotone convergence theory. Also, the standard stuff, work it out yourselves. I'm moving on. Okay, so now armed with that, we can actually prove that this formula holds. Let me call it 1. And then a proposition. Right. I have to trace a bit. So, proposition 1 says that this formula, which I've now called 1, that this is equal to this, holds, and also equal to this. Okay, now we have proposition 1 says that 1 holds in the sense that this is equal to that all the time. And we can define a measure on the product sigma algebra by this identity, and moreover, the measure so defined is unique. Finally, I got it right. Now, the proof is another stupid one, except for the uniqueness part. So, take E to be a product set, and then you just do the computation that gamma 1 of A times B is equal to what? Well, we have the picture here. Here should be an A, not a B that was wrong before. But, right, so you get a characteristic function with the value mu of B on A and 0 out elsewhere. So that's what I wrote here, and then you integrate that and get mu of A from the integral, and mu of B was constant. So that was what I erased here. So if E is a product set, you have that. And then vice versa, the same argument reversed, or the roles flipped, you see that this is also equal to gamma 2. So these two guys are identical on product sets. Okay, now next, okay, this isn't as good as the other ones, but now we need to prove that gamma 1 is a measure, and then of course analogously gamma 2 will be a measure. So now I make a claim Okay, and so either gamma 1 or gamma 2, if we apply that to the empty set, we get 0, so that's not hard. The difficult part is, of course, to verify that, let's take gamma 1. If I have an infinite union of sets EK, and they should be disjoint, then I have here an infinite sum. Like this, but that's just the monotone convergence theory. So let's say the left-hand side is equal to integral. So if I have many sets, so this is E1, here's E2, and so on, E3, and they are not, overlapping, and I do this EX guy, then, oh, sorry, E1X. Then yeah, I'm getting this, and then a bit of that, nothing of him. So you see that here you have mu of Ex, or infinite union, like this, the mu, and this, because mu is a measure, and these guys are disjoint, so I get infinite sum instead, using the fact that mu is a measure. And now it's just monotone convergence theorem or Beppe-Leva if you want to move that infinite sum outside. And once it's outside, we have the right hand side. Good, so gamma 1 defines then a measure, gamma 2 defines a measure, they coincide on the product sets. Does this mean that they are the same measure? This is a highly non-trivial question, it turns out, and it brings us back to some sins from the beginning of the course. It was not only completeness we skipped in chapter 1, and some other things here in 1.5. There was also this whole section 1.6 with the curious title Dinking classes. So here's the first time we see we're going to need them, and they're really just there because we need them for Fubini's theorem, but already at this point. So the corollary here, 164 or whatever, tells you that if two different measures coincide on the generating set of a sigma algebra, then they are the same on the sigma algebra. Feel free to think about it until next lecture, how you would go on about proving that, because then maybe you will appreciate this Dinking class business more. So next time, I will start off with, so now I just take that for granted, yeah? So next time, we'll continue. So what did we do today? Well, we defined product sigma algebra, and we defined product measures. So the definition is here. And for now, you just have to trust me that this one and this one gives the same thing. So next time, we're going to learn how to integrate, and in particular do Fubini's theorem, which says that, you can, if you have this two-variable integral in x and y against mu and u, you can do partial integration, basically. We're also going to see that lambda 2, the two-dimensional Lebesgue measure, is equal to the product of one-dimensional Lebesgue measure, at least if we stay on the Borel sigma algebra. But, so I'm sorry about this a bit disorganized class, but as time goes on, all things deteriorate, so do I. See you next time.